Okay, so good morning, everyone. We are recording now. So, are there any questions or concerns pertaining to anything we've discussed so far? Right, so let's just quickly summarize. We started with primal dual algorithms, which is our fifth module of this course. And we saw primal dual algorithm for shortest paths. And we also saw for minimum cost perfect matching, both in bipartite and in general graphs. Of course, in order to do that, we also needed to understand how to find a perfect matching in a graph, which we also did. We looked at these combinatorial algorithms for finding perfect matchings. Okay, so that's where we are right now. Um, so I think that will be all for primal dual algorithms as far as the lectures are concerned. You might be designing one on assignment 5. Okay, so let's switch our attention to a slightly different notion. So I want to start by recalling the following from your assignments. So given a graph G, yeah, there is some technical issue in the classroom, so I'm just gonna go a bit slowly. I'm gonna speak out everything I'm writing. So given a graph G, we talked about the perfect matching polytope, PMP of G, which is the convex hull of all the perfect matchings of G, where you view each perfect matching as the 0, 1 vector. Okay, so that's the perfect matching polytope. And we also talked about the fractional matching polytope, abbreviated as FMP of G, which is all the vectors in R to the number of edges of the graph that satisfy non-negativity and degree constraints. That message will go away automatically. You just turn it on, it will go away. Okay. All right. So those are the two objects that we've already studied previously, right? So the non-negativity constraints are simply that every edge, the xc is at least 0, and the degree constraints are simply saying that for each vertex of the graph, if you sum up all the x values for the edges incident at that vertex, then the sum will be exactly 1. Right? All right. And what is clear is that the perfect matching polytope is always a subset of the fractional matching polytope, because any vector that is a convex combination of perfect matchings will necessarily satisfy non-negativity and degree constraints. And what you proved on um, assignment 2, exercise 2, is that for bipartite graphs, they are exactly equal. Okay. So this is from assignment 2, exercise 2. Okay. In particular, so let's just get a visual sense of this, right? So the perfect matching polytope is some polytope. It's in higher dimensions, but I'm just drawing a two-dimensional figure here. And in theory, the fractional matching polytope could be some bigger object. It doesn't even have to look the same. It could be any bigger convex polyhedron, or in fact polytope in this case. And the extreme points of the perfect matching polytope are precisely the perfect matchings of the graph, right? Each perfect matching will be an extreme point and vice versa. Right? And in particular, what this result is saying is that in the case of bipartite graphs, the extreme points of the fractional matching polytope are also integral. They are also integer vectors. In particular, they are 0, 1 vectors. You won't get any fractional vectors or vectors which have any fractional component. Right? So, in particular, um, each extreme point of the fractional matching polytope of a bipartite graph is integral. In fact, in this particular case, they are going to be 0, 1. They are going to correspond exactly to the perfect matchings of the graph. Right? Okay, so I want to ask the more general question. Are there any sufficient conditions that guarantee that the polyhedron you're looking at has this property, that all the extreme points are integral? Okay, so that's the question we are going to ask today. So are there more general, rather than looking at just a specific polytope, the fractional matching polytope, we want to look at more general conditions that would guarantee this property. That imply that a polyhedron has this property. What is the property? Each extreme point is integral. Okay. If we can find such more general conditions, we might be able to just apply that to the bipartite fractional matching polytope and directly prove that the fractional matching polytope is necessarily integral, which you already did on an assignment, but you focus specifically on the perfect matchings of a bipartite graph, right? In fact, you looked at an even cycle and you tried to show that it can be written as a convex combination of two other points, right? So it was very specific to bipartite graphs and perfect matchings. Okay. Are there any questions or concerns at this point? All right. So if not, let's define a polyhedron is integral if all of its extreme points are integral. Right? When I say an extreme point is integral, what I mean is that the vector corresponding to that extreme point is an integer vector. All the entries are integers. Okay. Okay, so we are looking for sufficient conditions that will guarantee that a certain polyhedron is integral. Okay, so let's make it more precise. So typically when we are discussing geometry, we just wrote down a polyhedron as the finite intersection of as the intersection of a finite number of half spaces. Right? So given a polyhedron P, so it's all the vectors in Rn such that Ax is less than or equal to B, where A is an M cross N matrix and the dimensions of the rest are clear from this. Right, so given a polyhedron like this, are there sufficient conditions on A and B, because that's what is defining our polytope, that imply that the polyhedron is integral. Rather than imply, let me make it even clearer. They guarantee. All right. So as you expect, the answer is yes. Turns out there are special matrices which pop up everywhere in combinatorial optimization that would imply such results. Right? So a matrix A, I'll put this in a box to distinguish from the article, is totally unimodular and we'll abbreviate this to simply TU. If you look at any square submatrix, its determinant should be 0, +1, or -1. If for each square submatrix, say M, the determinant of M is either 0 or +1 or -1. Yeah, I should for each square submatrices the strokes, right? So a submatrix is simply something you get by selecting an equal number of rows and equal number of columns, or by deleting an equal number of rows and equal number of columns, right? Observe that we are saying this for every square submatrix, right? That also includes the matrices that are 1 cross 1. So in particular, it immediately implies that all the entries of these matrices have to be 0 +1 or -1. Exactly. So note that this implies that each entry of A belongs to 0 +1 -1. However, the converse is not true. If you take any matrix which has just zeros, +1s, and -1s, it does not necessarily mean that the matrix is totally unimodular. In fact, I'll give this as a do it yourself. Find a 0 +1 -1 matrix. Right, so all entries are from this, such that A is not totally unimodular. Okay. All right. So if our matrices have this property, then it turns out, with one more assumption, which is that the right-hand side vector B is integral, we can claim that all the extreme points of the polyhedron will be integral. Okay. All right. So yeah, let's see. Let's move on to a new page. So here is a theorem. If I'm not mistaken, this is a theorem due to Hoffman and Kruskal from 1950s. I'm not sure. Anyways, it's theorem 6.26 in CCPS, and I think it is due to Hoffman and Kruskal, probably independently. Okay, so it says that, let's suppose A is an M cross N totally unimodular matrix, and let's say B is an integral vector of the right dimensions. Then the polyhedron P, which is all the points in Rn that satisfy Ax less than equal to B, is integral. All right. Yeah. So let's prove this. Okay. So our goal is to show that each extreme point x bar is integral, extreme point of this polyhedron. Okay. So let's start with any extreme point. Let x bar denote an extreme point of the polyhedron. And let's see how we can show that every component of this vector will be an integer. We are going to use a bunch of things. Well, basically one thing that we have proved earlier about extreme points. And then we are going to use Kramer's rule from linear algebra. Okay. All right. So do we know of a characterization of extreme points? Does anyone recall a characterization of extreme points? Right. But a more algebraic one. So that's a very geometric one. Right. So I think you are going towards, sorry, rank. Did I hear rank? Yes. Can you tell me what is the rank characterization? Yeah. So we have a characterization in terms of the rank of the matrix or rank of a certain matrix. What is that certain matrix that we are looking at? Right. So think about tight matrix. Exactly. Right. So if you look at the rank of the tight matrix corresponding to this point, its rank should be n. Right. So by theorem 2.20, from GKT, we know that the rank of the tight matrix corresponding to this point x bar is exactly equal to n. Right? What does that mean? Let's try to see what's going on. So we have some number of constraints and we have some number of variables, and we are looking at the tight constraints, and that is going to be an n by n matrix in particular. It's a full rank matrix, so we are taking all the n columns, therefore we have exactly n rows, and that will be a full rank matrix. Right? So this is going to be our tight matrix. Okay. So in particular, the tight matrix is an invertible squared matrix. Right? In fact, a square submatrix of the given matrix A. That means what can we say about its determinant? By the assumptions we have. It's +1 or -1, right? That in particular implies that the determinant of the tight matrix is either +1 or -1. Okay. All right. So now let's recall Kramer's rule. To be honest, I didn't even recall, so I had to look it up. By Kramer's rule from linear algebra, you can compute each entry xi bar as follows. So what you do is you take the determinant of the tight matrix, except that you have to replace the column I. So we are looking at the ith entry. So we are going to replace the ith column by the right hand side vector, which is B tight. So we are going to take the vector of the subvector of B, which corresponds to the tight constraints. And that divided by determinant of the A tight matrix. All right. So just to give you notation, this is, maybe I should say, the inside part here. It's the A tight matrix where the ith column is replaced by the vector B tight. Okay, that's just notation. Observe that this matrix here is an integral matrix, right? Because we know that the original matrix is a TU matrix, so all its entries are +1, 0, -1, and the B vector we have assumed is an integral vector. So the entire matrix is an integral matrix, right? And that implies that its determinant is going to be an integer, right? If you just go to the determinant formula, you can see that the determinant is an integer, and um, the denominator is +1 or -1. So the whole thing is an integer, right? Great. Since so I'll just say, since this is integral, determinant is an integer, and this implies that xi bar is an integer. So each component is an integer, which means that the vector is integral. All right. So this gives us a nice condition, a nice sufficient condition for a polyhedron to be integral. And it turns out that it is immensely useful. Most results in polyhedral combinatorics, which is the more specific thing that we are studying right now, where you get that the polytope or the polyhedron is integral, they are generally implications of the Hofmann-Kruskal theorem or similar other results which can be proved in a similar fashion. Right, so I'm going to state one more without proof, but that's going to be very similar to this, so you can try it on your own. Right. So for most of them, this is the way you go about proving that the polyhedron is integral. The one exception is Edmond's perfect matching polytope theorem. Right, so we know that for non-bipartite graphs, the non-negativity and degree constraints, they do not capture the perfect matching polytope. We also need these odd cut constraints. And the fact that once you have the odd cut constraints, you get exactly the perfect matching polytope, apparently this cannot be explained by the Hofmann-Kruskal theorem or similar results. So there you actually need to really delve into the perfect matchings of a graph and explain why this is true. Right? So you really need some combinatorial ideas. Whereas here, it's largely just algebraic. You just need to basically show that the matrices involved in your polyhedron definition and the vectors satisfy these properties. Right? Once you have these properties, everything else comes for free. Okay. All right, so I just want to state one more result in the same spirit, and I don't think I'm going to have much more material for today actually. I was not expecting this to be so fast. Okay, so yeah, so it's a very similar result. I'm just going to state it from GKT, and we will use it for max flow min cut, which I'm going to start on Wednesday. Okay, so a similar result. This is Theorem 5.10 from GKT. All right, so it goes as follows. Let's say A is a TU matrix. Then it says that all of the following LPs are integral. In particular, the feasible region will be an integral polytope or polyhedron more generally. Okay, so then each of the following, maybe I should make it more precise. The feasible region of each of the following LPs is integral. All right, so the first one is maximize C transpose X such that AX equals B and X is non-negative. So this is a standard equality form LP, right? And we need to assume that the right-hand side, B, is integral, right? So the fact that AU is a TU matrix is true for all the statements. In addition to that, we will also need certain vectors to be integral vectors, right? Second one, observe that whether a polyhedron is integral has nothing to do with the objective function, right? The objective function is irrelevant. We are just talking about the feasible region. So it makes sense that we don't care about that C vector to be integral. Okay. Next one. So these particular LPs are going to show up. These particular types of LPs are going to show up when we discuss max flow min cut, which is why I'm stating this theorem as it is. So now consider the following. Maximize D transpose X subject to AX equals 0 and X is bounded between 0 and C vector. Right? So this just means that every entry of X is bounded between 0 and C for the corresponding C for that component. Okay, and here we need to assume that this vector C is integral because it is in the constraints. All right. And third one is minimize C transpose L subject to A transpose Y plus L is at least D and L is a non-negative vector. And here we again have to assume that D is going to be D and yeah, D is going to be integral. Yeah. Okay, good. So yeah, so here the L's are variables, right? The L vector is actually variables. And so is the Y vector. Okay. So it turns out that all of these forms of LPs will also be the corresponding feasible regions will be integral polyhedrons. the proof approach is actually quite straightforward. So basically you prove this result using the basics, right? You basically show that you're taking a extreme point, which is going to be a basic feasible solution, and then you apply, instead of looking at the rank of the tight matrix, well, again in the basic feasible solution, you will get the basis variables and the non-basis variables. Again, you'll get a basis in the matrix and the non-basic columns, right? And you use the same ideas as before along with Kramer's rule, right? Prove using same ideas as before. Basic feasible solution plus Kramer's rule. Okay. And for these two other LPs, you first convert them into standard equality form and then you apply first result. That's basically the idea. Okay. Yeah. You also need some other matrix observations, one of which I'm going to put on the assignment 5. So if you have a totally unimodular matrix, what you can do is you can put the identity matrix below it. So let's say A is a totally unimodular matrix. Then you can consider the following matrix, where I'm going to put the identity matrix below it, and I claim that this is also totally unimodular. Okay, so you need those kinds of results as well. Plus TU matrix results. Okay, so it's just proving them is going to be a bit of a boring thing. It's going to be similar to what we just did. So I don't see the value being added in there. All right. So we are going to use this to look at max flow min cut and prove the max flow min cut theorem, which you may or may not have seen in previous courses. So we will go through the necessary background and prove this. And we'll also see an algorithm for max flow min cut, which is probably also something that you might have seen in other courses. Right, but we will focus on the integrality properties a bit more than the algorithm. The algorithm is the famous Ford-Fulkerson algorithm. Right. What else do I want to mention? Yeah. So observe that essentially this first condition here, if you look at the first LP, it looks exactly like the perfect matching, fractional matching polytope, right? So you have the degree constraints, which are the equality matrix, and you have the non-negativity constraints. So in fact, it follows from theorem 5.10 that for a bipartite graph, you need one more thing. You need that the vertex edge incidence matrix of a bipartite graph is totally unimodular. This is something we'll be proving on assignment 5. So I'm not going to prove it here. So this is on assignment 5. Prove that the vertex edge incidence matrix of a bipartite graph is totally unimodular. So if you assume this and you use 5.10 first result, then it tells you that the feasible region of the fractional matching polytope is actually an integral polyhedron for bipartite graphs. Right? So these two imply that the feasible FMP of G is equal to the perfect matching polytope of G for bipartite graphs. Right? So notice that you are not explicitly using the, in some sense, you are not doing very specific manipulations. You're not taking a point and then showing it to be a convex combination based on the even cycles. Of course, the even cycles are going to be used somewhere, right? The fact that the bipartite graph does not have odd cycles has to be used somewhere. And the place it will be used is to show that the matrix is totally unimodular, right? So there you can actually, the fact that the graph is bipartite, which means that the vertices can be colored black and white so that all edges go from black vertex to white vertex, that can be used to show that the matrix is totally unimodular. And the same thing does not hold for non-bipartite graphs, right? So of course, at some point the bipartite structure has to be used, but this is a slightly more general way of doing it without worrying too much about the perfect matchings, just looking at the bipartite structure. Yeah. Okay. And the same way, we will be proving that the max flow min cut theorem holds, for which we'll be using this theorem 5.10. Okay. Good. So I think that is all I have for today. It's a slightly shorter lecture because the last one was ridiculously long. Are there any questions or concerns? Anybody in the call? Varun, you're there?
Yes, sir.
Okay. Madhav, Jude, Vishal? Okay. If you have any questions, please raise them. Otherwise, feel free to leave the meeting. We are done for today's lecture. Okay, so I'm going to stop recording now.